Welcome to Hartman Math. This is lesson 4.1. We're looking at exponent properties. So we've got a problem, how we would expand it through expansion, and how we simplify to get our answer. So for example, just the first one through x squared times x to the third. X squared means x times x. X to the third means x times x times x. So we've got a total of 5 x's being multiplied. So our answer is x to the 5th power. So if our problem was x times x squared, what would be the expansion? Well, first, x means x to the 1st power. And then the expansion is a single x times 2 x's being multiplied. So our simplified answer, there's a total of 3 x's being multiplied, x to the 3rd power. If this is the expansion, what was the problem? Y to the 4th times y to the 3rd. And the answer is a total of 7 y's being multiplied, y to the 7th power. Answer is a to the 8th power. The problem was a to what power times a to the 3rd power. We would need 5 a's multiplied by 3 a's to get a to the 8th power. And then the expansion becomes 5 a's multiplied by 3 a's. Our answer is 3 to the 9th power. We've got 3 times 3 as part of the expansion. What's the other part of the expansion? Well, that's 2 3's being multiplied. We need 7 more. So our problem was 3 to the 7th times 3 to the 2nd. So if our problem is x to the 5th times x to the 6th, without actually expanding, but just visualizing in your mind the number of x's in each factor and producing, what do you think we get here as our simplified product? You would x to the 11th, 5 x's multiplied by 6 more x's, x to the 11th power. What if it was I to the 50th times I to the 30th? What's our product? I to the 80th. And the last one is actually our rule. If we're doing a to the m times a to the n, we're going to get, well, how have we been doing these? To go from there to there, we're adding the exponent, keeping the base. So we would get a to the power of m plus n. All right, this time we're looking at quotient of power property. So same thing, just looking at a little division. Our problem is x to the 6th divided by x to the 4th. 6 x's in the numerator, 4 x's in the denominator. And essentially our x's we're going to kind of cancel here because x divided by x, anything divided by itself, 7 divided by 7 is 1. We're going to get a bunch of 1's that cancel out. So cancel, 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 cancel. We're left on top with 2 x's being multiplied, and that's x squared. So our problem is 7 to the 5th divided by 7 to the 2nd. See what we get for expansion. It'd be a good idea to write these with the multiplication dot. And again, we're going to cancel. We're going to cancel 7 times 7 times 7 is 7 to the power of 3. And then based on that being a number, what would that equal? We could go to our calculator, 7 raised to the 3rd power. We're going to get 343. So if it is a number, we're going to want to simplify that. Here's our expansion, what was the problem? H times h times h times h to the fourth power divided by h to the third power. Think about the canceling. We're just going to get a single h to the first power, but we would not need to write that 1 as an exponent. Now working backwards, if our answer is n to the fifth, that would be, as a problem, n to the sixth divided by n to the what power? The answer is 1. So our expansion would be 6 n's on top, 1 n on the bottom. Because 1 n is going to cancel with the 1 n, we're going to be left with 5 n to the fifth. Kind of one more like that before we kind of change it up just a little bit. We got x to the 80th divided by x to the 50th. What do you think is going to be our quotient? Well, if we've got 80 x's on top and 50 x's on the bottom, these 50 will cancel with 50 of those. How many are left? 30 are left. X to the 30th power is our answer. We want to look at what happens when there are more of the variables on the bottom. So in the expansion, b times b on top, 6b's being multiplied on the bottom. Again, cancel, cancel. We're left with b to the fourth power on the bottom in the denominator. What's on top? Well, b times b is the same thing as b times 1. So we'll be left with a 1 as the numerator. If our answer was 1 over r squared, and we had 7 r's on the bottom being multiplied, how many r's would there be on the top being multiplied? There would be 5. Expansion would look like this, so that all 5 of these cancel with 5 of these, leaving 2 r's being multiplied on the bottom. So what's the quotient? Visualize. Again, this is now our rule for the quotient of power property. We have a to the m divided by a to the n. We can see how we're creating this by taking a single base and then subtracting the exponents. So our property a to the power of m minus n. We're now looking at power of product properties. So we're taking a product, 3 times x squared, raising that to a power. Squaring means multiplying by itself. So we've got 3x squared times 1 more 3x squared. 3 times 3 is 3 squared. X squared times x squared, we learned in the first slide, would be add the exponents, x to the fourth power, and then 3 squared is just 9, so that's the fully simplified answer. All right, what about this one? Here's our problem. It says to square it, the expansion, squaring means multiply by itself. 4 times 4 means 4 squared. X to the third times x to the third. Multiplying with like bases, we add the exponent, so that's x to the sixth. Y times y is y squared. And 4 squared is 16, so final answer right there. 2EF squared, all raised to the third power. Raising to the third power means we need this factor 3 times. So that times itself again. 2 times 2 times 2 means 2 to the third power. E times E times E, e to the third power. F squared times F squared times F squared. That's a total of 6F's being multiplied. That is F to the sixth power. 2 to the third power is 8. All right, here's our expansion. What was the problem? We have 3 identical factors. So here's the base, raised to the power of 3. simplify answer, 5 times 5 times 5 is 5 to the third power, x to the fourth, x to the fourth, x to the fourth. That's a total of 12 x's, so x to the 12th. 5 to the third power is 125. This might be a little trickier. Here's our answer. Here's our expansion. Something was identical, 3 identical factors. So if it's 3 identical factors, there's 3 3's, so it's a 3 in each. And then to get I to the 6th, they have to be the same in each. I squared, I squared, I squared. J to the 12th, to be the same in each, it's going to be j to the 4th. That makes a total of 12 j's. That makes a total of 6 i's. So the original problem was this, and there's 3 of them, to the third power. All right, so visualize, what does this turn out to be based on this problem getting to this answer? 2 gets raised to the 10th, x gets raised to the 10th, y squared gets raised to the 10th, meaning that we multiply the exponents. 4 became 12 by multiplying by the 3 here. So 2 to the 10th, x to the 10th, y to the 20th. And then our rule, AB raised to the power of m, is that when we're raising a product to a power, each factor just gets raised to that power. So it's a to the power of m times b to the power of m. Similar ideas when we're dealing with quotient of, should say, power of quotient property. So we've got a quotient, a fraction, raised to a power. It's really just the same idea. So squaring means there's 2 of them. Multiply everything in the numerator, multiply everything in the denominator, and simplify. So the expansion here, we're going to have this quotient. We're going to need 3 of them being multiplied together. And then how would we multiply that out? Z times z times z, z to the 3rd. 5 times 5 times 5, 5 to the 3rd. X cubed, x cubed, x cubed makes x to the 9th. 3 x's, 3 more x's, 3 more x's, that makes a total of 9 x's, x to the 9th. X is not y's. All right, here's our problem. Without writing it out in the expansion, what do we get? Same idea. We get 2 to the 9th. I cubed to the 9th means we're going to multiply those exponents. K to the 9th on the bottom. 2 to the 9th on your calculator is 512. So as a general rule, again, when raising quotient or product to a power, just take each part, numerator and denominator, raise to that power, a to the power of m over b to the power of m. So a couple of introducing the negative exponent property, a to the negative m. The negative really just indicates reciprocal, so it's just going to turn out to be 1 over a to the positive m power. It works the same this way, so if it's 1 over a to the negative m, we're going to do the reciprocal, negative meaning reciprocal, so if it was on the bottom, it now flips up to the top as a to the m positive on top. So that's the negative exponent property. Sometimes we'll just say it's a level change. So this one, not a fraction, we consider it to be on top. Change the exponent to positive, change its level to the bottom. If it was on the bottom, it goes to the top. So some practice problems here. 3 to the negative 6th follows this model. 1 over 3 to the 6th, which means 1 over, and if you type in 3 to the 6th on your calculator, you get 729. What about this one? Again, kind of think of this idea of level change. If it has a negative exponent, it's part of a quotient and or product, no addition or subtraction, it's going to level change. So the r's on top, they're going to go to the bottom. Exponent changes to positive. The 2's, they have a negative exponent. They're going to go to the top. Exponent changes to positive. The s's do not have a negative exponent. They're going to stay where they're at. So as I said, the 2's go to the top. The r's go to the bottom. The s's, because they had a positive exponent, stay where they were. 2 to the 3rd power is 8. The 0 exponent property, and you can try this on your calculator. Let's just say A represents, it's a variable, so it represents a number, it represents a value. Let's say it's 7. On your calculator, try 7 raised to the 0 power. You might be a little bit surprised on what you get. Get 1. So any number that's raised to the 0 power, the answer is always 1. It's the 0 exponent property. So let's see if we can illustrate it here. What is 6 to the power of 0? 1. What is 6 times x raised to the power of 0? Well, assuming x is just a number multiplied by 6, we're going to get another number raised to the power of 0. We get 1. Looks similar. Would we get the same answer? Well, by the order of operations, the 0 as an exponent applies to the x only. What is x to the power of 0? 1. Then we multiply by the 6. 6 times 1. That one we get 6 because we had to do x to the 0 first, then multiply by the 6. All right. I'm going to pause here, take a moment, write these down, see what you do is simplify, and we'll come back and discuss. First one, we're dealing with a quotient raised to a power. So we take the numerator and raise to that power, the denominator and raise to that power. Then comes the negative exponent property. If it has a negative exponent, it's going to level change. So the 1's are going to go to the bottom, turn the exponent positive. 4's go to the top. 4 to the 3rd power is 64. 1 to the 3rd power is 1. 64 divided by 1 is our answer, 64. So this next one, maybe we just start with the 9 over 18 part, reduce that, just a normal fraction, divide them both by 9, we get 1 over 2. Then with the x's, we know the rule there when we're dividing with like bases, just to subtract the exponents. But an easier way might be to look at this and say, well, I've got some x's on the top and I've got some x's on the bottom, so there's going to be some canceling. Are there more x's on top or more x's on the bottom? On the bottom. How many more? 1. So the x's, x to the 1st power, land on the bottom. Here we've got a negative exponent. That's going to mean level change. So the y's are going to change level. They're going to go to the top. Exponent changes to become positive. So now, I don't think we really need the 1 here, because we do have something on top, and we don't need an exponent of 1. So our final answer could be y squared over 2x. And that's it for today. I'll see you next time.